In this question, I'm asking you to propose a synthesis of this alkene molecule by using alcohols of 6 carbons or less. What that means is that all of these carbons in this final product must have come from some sort of alcohol made of 6 carbons or less. All right, so again, let's work backwards. We're just going to focus on what functional group we have here, and we can see that we have an alkene here. We're going to ask ourselves, how can we make an alkene? Well, you know you can make an alkene by doing an E1 reaction or an E2 reaction. Also, we're allowed to start with alcohols of 6 carbons or less, but we can see this molecule has a lot more carbon-carbon bonds than we're allowed to start with. That should tell you that you're probably going to use some carbon-carbon bond forming reactions using things like Grignards or organolithiums. Now, keep in mind, every time you do those reactions with Grignards or organolithiums, you're typically doing them to some sort of electrophile, like an aldehyde or a ketone. The result is always some sort of alcohol. So what we're going to do here is we're going to try to work our way back to alcohols. And when we get back to an alcohol, that's a moment where we're going to try to split this thing apart. Because remember, Grignards with ketones make alcohols. Grignards with aldehydes make alcohols. So we're going to try to work this back so we can get to these alcohols of 6 carbons or less. But we'll start with the functional group we can see, the alkene. So I'm going to draw the arrow from the product here. And I'm just asking myself, how can I make an alkene? Well, I could do an E2 reaction. So let's draw this potential substrate that was used in this step. Well, what do we need when we do an E2 reaction? We need some sort of leaving group. We also need a strong base. Well, the question is, where are we going to put that leaving group? I'm kind of looking at this and knowing that this is a 5 carbon entity. This is a 5 carbon ring with a 2 carbon chain. I probably want to split at this bond right here. But what I want to do is at some point, I want the alcohol to be on this carbon right here. So what I'm probably going to put here is a bromine or a chlorine, something right there. The goal is I'm basically saying to myself, I want the functionality to be at that carbon because if I can get the alcohol back to that carbon, that's where I can split that bond. All right, so in order to do this E2 reaction, if I want to maximize the amount of E2, I'm going to go ahead and use a sterically crowded base here, something like T-butoxide. That'll do the elimination reaction, kicking out that bromine and forming that alkene. Now I'm going to focus on this bromine product, keeping in mind that I'm trying to work my way back to an alcohol so that I can eventually split this bond right here. So the question is, how can I make this brominated product? Can I do it directly from an alcohol? And the answer is yes, I can. I could have potentially had this alcohol. I'm going to put that hydroxyl group right there. Now, the question is, how can I convert that alcohol into that brominated product? What reagent would I use? Well, because it's already tertiary, we don't really have to worry about shifting. So I'm just going to go ahead and use something like HBr. Now I'm going to focus on this alcohol. And again, we wanted to get back to the alcohol because this is a moment where we can take advantage of splitting this in half. So I want to split this bond right here, which means everything to the right side must have been my ketone in this case. Because remember, organometallics with a ketone always make a tertiary alcohol. This is a tertiary alcohol. This carbon-oxygen bond must have at one time been the carbon-oxygen double bond until this bond was formed and reduced it. So everything on the right side here must have been the ketone, which means that the ketone I had must have been something like cyclopentanone. Don't worry that you don't know how to name that yet. Everything on the left side here must have been the nucleophile, the Grignard in this case, and it must have been nucleophilic at this carbon right here. So that's where I'm going to put the magnesium. So here's that Grignard reagent, and I'm just going to go ahead and randomly choose bromine. You could pick chlorine or iodine, it's up to you. And then when those two things reacted with each other, there was a second step where we threw in the acidic workup, and that's what put this proton on the final alcohol there. So now we have these two starting materials, and we still have to work our way back to alcohols. Well, let's start with this ketone. And I'm just asking myself, how can I make a ketone? Well, ketones are made when you oxidize secondary alcohols. So there's a secondary alcohol. I'm going to oxidize that. I can use the Jones oxidation or the PCC method. Both will result in that ketone. So this is a permitted starting material. It's an alcohol of 5 carbons or less, so that one's good. Now now we're going to work our way back from this Grignard reagent back to an alcohol. Again, I'm already looking at this thing and thinking it has 7 carbons. I'm only allowed to start with 6 carbon alcohols, which means I probably had to have used another organometallic at some point in order to make a new carbon-carbon bond. Pretty much, it's probably going to be this 5 carbon entity reacting with this 2 carbon entity, which means at some point this must have been a new bond right here. But we'll get there. The point is, I'm trying to work my way back to an alcohol because that allows me to get to another point where I can split this in half. All right, so I'm just asking myself, how can I make this Grignard reagent? Well, Grignards are always made from the corresponding haloalkane. So I'm just going to put that bromine back on that carbon using magnesium metal and some sort of, usually an ether solvent, but those reagents will convert that haloalkane to that Grignard reagent. Now I have the bromine on this carbon here, and that's good because eventually I want this to be the new bond, and which means there must have been a hydroxyl group here at some point and not a bromine. So let's draw that corresponding alcohol. So now I have this alcohol molecule here, which means this must have at one time been a carbon-oxygen double bond until this ethyl group, this carbon specifically, came in and formed this bond and reduced it. So now that I have an alcohol, this is a good moment for me to split this thing apart. So everything to the bottom of this bond right here, the side with the oxygen, that must have been my ketone because again, it's a tertiary alcohol. So I must have started with some sort of ketone. Again, that's cyclopentanone. And we already showed how we make that from the alcohol, so we don't need to do it again. But what Grignard did I use? Well, it's a 2 carbon entity. The Grignard must have had the magnesium bonded at this carbon here, which means I must have had something like magnesium, and I'm just randomly going to choose chlorine here. You could have chose bromine or iodine, however you decide to make this. But that's our Grignard reagent. We got to work that back to an alcohol still. Well, again, I'm just asking myself, how can I make a Grignard reagent? I must have had some sort of chloroethane, because I'm using chlorine in this case. I use magnesium metal and an ether solvent in order to make that conversion. But I have this chloroethane, which I have to make from an alcohol of 6 carbons or less. Well, I can make that directly from ethanol, and there's a lot of different ways I can do that. I can use HCl. That's one thing I can use. It's a little sluggish in this case, but you can use it. Or you could have used something like SOCl2, those thionyl-chlorides. Those are fine to use as well. That would work. Could use something like PCl3 here. Any one of those would have been fine, but we're back to ethanol, a permitted starting material, and this is a proper synthesis in order to make that specific alkene.